Can you hear me? Hello? Hello? Can you hear me? Hello? Can you hear me? Hello? Hello? Sita, can you hear me? Hello?
Yes, sir.
Okay, can you see the screen?
No,
Is this
yes, sir. Yes, sir.
okay? I will wait for a few minutes to see that. Can you see it? Hello? Can you see it? Hello?
Yes, sir.
Yes, sir.
Okay, let me start with that. Well, I have taught you separation axioms. Continuing. I will tell you that why we need to do it. It's called separation axioms or properties. Look, until now I have done two, T1 and T2. Okay, T2 means Hausdorff. And yesterday I talked about that. But look, here, the points, we are separating the points. Actually, we are separating the points. T1 we have the weak separation, T2 we have the strong separation. Why are you interested in separating points? That I will come. That I will tell. But suppose points in a Hausdorff space, in a T1 space, points are closed. Points in a T1 space are closed. Okay. Now suppose I don't take 2 points. I take one. I have a topological space. and I take one closed set. See, closed, and a point outside C, that makes minus C. Okay, so I am replacing basically points by one point by closed set. You can say, why don't you take two closed sets? That we will also take. So here, so C and this pair, then when it can be separated, when they can be separated by open sets, and when they can be separated by continuous functions. I told you yesterday the continuous function, separation by continuous function is stronger than open sets. If you have separation by continuous functions, you will have separated by open set, but not vice versa. Now the thing is that, okay, so this is the thing. First I'm taking one closed set and outside this. Thing is, yes, we here that is the first thing. This is we need what is called regular. I will tell you also that why we need regular complete. And when it can be separated by continuous functions, then it is completely regular. I will give the definitions. Okay, right. And then what about this normal? Normal is that here if you take two closed sets, that means of course disjoint. Suppose you take another closed set. This is also closed and they are disjoint. This is the thing again. Now you can ask. The good thing is that in case of this situation, when we have this so-called, these two will be the same. When in case of two disjoint closed sets, these two will be same. Okay, so that we do not need to bother about whether it's separating by open set or continuous function. This is essentially due to Eurytion's lemma. It is actually a big result. It should be called theorem. And you can go to the net to see that Eurytion had a short life. Otherwise, he could do a lot of topology. So this is actually related to called normal space. Okay, so regular, complete regular, normal. Okay, but I won't put much emphasis on that. My emphasis will be these two because these are related to analysis also. Okay, regular I will just mention in passing so that you understand this thing. Now, so that basically 5 separation axioms comes. T1, T2, regular, complete regular, normal. There are some other separation axioms, they are not that important. Okay. Now the thing is that why we do it, first of all. Great thing is that when given a topological space, of course, if it is a metric space, it's nice. If it is not a metric space, then we would like to see that how much it is different from a metric space, whether certain properties in metric space we use that we have here or not, though it is not a metric space. Okay, if we have them, then many things what we did for metric space we can do here. Thing is that metric space has all these properties: T1, T2, regular, complete regular, normal. Everything is there. That's why the reason on that. Another reason I will tell you later on. So that first of all, separation by continuous functions into Ali Prantis Barkinsa, you should start looking for article 10, page 80. You can read that, but 82. 86 if you want, but I will tell you that. Okay. Separation by continuous functions. Now look, I talked about metric space. So let's start with the metric space of that. You already know if you have a Hausdorff space, it will be 2, 1. Already know two distinct points can be separated. If you have two distinct points here, and if dxy equal to 2r, then you know these are disjoint. Sorry, dxy. Then bxr, byr are disjoint. Open balls are open sets. So this is Hausdorff. If it is Hausdorff, it is 2, 1. Now suppose you have a closed set. Now before that, you see that a subset of x, of course you can assume a non-empty, then dxa is a function, it's a continuous function. In fact, look, x belongs to x. So if you take a function xt to this, function is this, given a. So actually it should be fa called. Okay, a is given. Okay, so fa x is dxa. Now you see that you last semester did dxa minus dya is less than equal to dxy. Actually, this is something stronger. That means fa is uniformly continuous. Don't forget that this is very important for metric space. Fa, just now Alphonse said he has given example here. They have used example as this for metric space. So it is uniformly continuous. Now look, this fa function, fa x is dxa. Where closed set is coming, that I obtained. Now we also know that dxa is 0 if and only if x belongs to a bar. Okay, this we have proved last semester. Now, so if a is closed, now we take a is closed. If a is closed, then dxa is 0 if and only if x belongs to a. Now look, with this, if you take C is closed subset, that is A equal to C, C is closed, and take x belongs to x minus c. Okay, look, this is a function. Look, if you take now fc function, look, fc, take y here outside, fcx equal to dc xa, x c actually, sorry, fc equal to this. Okay. Then you see that fc x is 0 for all x belongs to c, and fc y not equal to 0, but actually greater than 0. So you are being able to separate this closed set C and the point y not lying in this by a continuous functions. So obviously you will be able to separate it by open sets, because separation by continuous functions is stronger. You can take 0 and fcy. So you can take an open set here. Like if you take the function, you take open set 0, Take any open set. Minus half to half FCY. FCY is greater than 0. So distance. The inverse image, it will contain, C will be contained in this. FC inverse. This is an open set. And FCY, you can take that. FCY will be contained in half FCY. Can take 3 by 2 FCY. Okay. So this will be, if you can separate by a continuous function, you can separate it by open sets, not vice versa. So here you close set at a point lying outside, you can do it. Okay, separating them. But what about, so I said regular, complete regular, that I will give you the formal definition. Regular regular is separate by open sets, complete regular is separate by continuous functions. In case of, so this is stronger than this. So in case of metric space, we can separate by continuous functions. So it is done. Now, if you have two disjoint closed sets, okay, well, and of course, if you want to have something, a function, continuous function to going to 0, 1, that will do later on. We can modify a little bit. Now, suppose you have two disjoint closed sets. Two disjoint closed sets. Suppose A, B, AB closed. Of course, I take non-empty. For empty set, I don't need to do it. Closed, basically, you need, it is understood. So, non-empty sets in X. Okay, right. Now look, simple function I will take that, give the function g xt to r. Look what I will do. First thing I can do that gx equal to dxa plus dxp. समझ गया? Closed sets. Now look, if x belongs to A, then dxa is 0. Then gx equal to dxp. Okay. If x belongs to A implies, x belongs to B implies, okay, gx equal to dxa. Well, but how would I know that they are different? What I need to know, okay, that basically when I separate two disjoint closed sets, I need to have something, it will be better if I get, suppose GA equal to 0 and GB equal to 1. Okay, right. I do not know they are different or not, but this much I am getting, apparently. But if I can make them different somehow, then it will be all right. Look, there is a trick that I can do. What I will do that? Okay, let me tell you that. What I will do. I will write this. First of all, this is a real value. So less than equal to 1, but you should know denominator is never 0. Look, if denominator is 0, these are non-negative things. Both will have to be 0. That means x will have to be the A intersection B. But this is not disjoint. So that denominator is never 0. So this is well defined. Okay, right? and is lying in between, value lying in between 0 and 1. Okay, look, if you have now x belongs to A, then this is 0. Okay, so that gx equal to 0. That is on A, GA is 0. And if x belongs to B, okay, then this is 0. So that this is, look, if this is 0, then dx is coming. That is not 0. This is 1. That means GB is 1. And this is a continuous function because this is a continuous function, real valued continuous function. You can prove that. This is sum of two continuous function is continuous function. Denominator is never 0. So this will be also continuous function. That you can prove that in Yang. Okay, right? So that this will be a continuous function. And look, on GA it is 0 or GB equal to 1. We can strictly separate. Actually, with this I could work a little bit also, but this is the easiest way to do it. So in case of metric space, I can do the disjoint closed sets. I can separate by a continuous functions. So this is related to normality. Okay, and I told you normality is separation by open sets and separation by functions. That's same due to Eurytion's lemma. So these things we want to do in JAL. We want to JAL so that you don't need to assume a space to be metric space. In fact, why you say why you do not work in metric space and that? Often we get nice topological spaces which are not metric spaces. Look, if you go for application, you'll have to see what it's not what you wish to have. You'll have to work with what you have. Okay, like let me tell you something that suppose like a theorem I have seen. First, let me tell you about the result. Suppose you have 4 hypotheses. And you can prove a good result, the conclusion, good conclusion. You have a strong conclusion. You may think that, oh, I have got a good result with these assumptions. But the thing is that when you start using it, then you say that in your situation, very rare you get that 4 hypotheses you have assumed that satisfied. At most 3, and in fact, probably often 2. Then you say, oh, it is useless. That's why if you go for 3 or 2 hypotheses, you may not get that strong conclusion. You get something weaker conclusion. Similarly, if you 2 hypotheses, still probably you have some weaker conclusion. But still they are good because like 2 hypotheses, you often see, oh, 2 hypotheses, I'm assuming they are often satisfied. So I can at least have this conclusion. So that is also, that is, should be your philosophy that if you have less with less, how much you can work. It's not with more you can work. Philosophy should be with less. How much you can work. If you have that, then it will be applicable in wide areas. So between metric space and Yarn topological spaces, that is also the difference. Often you do not have the metric space. Suddenly you see certain space I'm getting. This is not a metric space, it is topological space. But where I can use this topology, what properties it can have. Okay, that's why we are doing a Hausdorff regular, complete regular, normal. Depending on the situation, what you get, still you can do. Like normal among them is the strongest one basically. If you have a normal space, normal Hausdorff particularly, then you can do many things as you do for metric spaces. So that's the idea. Another thing I will tell you that. So first, let me give you the definition of regular space. That is another reason why it is important. So definition, look, a topological space X tau is called regular. If given the non-empty closed set, empty closed set you don't need to do it. Closed set C in X, and this is given, and X belongs to X minus C. There exist open sets U and phi in X tau such that C is contained in U, X is contained in phi, and we are disjoint. That means we are having separation by open sets. Okay, we are separating a closed set and a point. This is called regular. Okay, now look, this need not be T1, need not be Hausdorff. A regular space need not be T1 or T2 Hausdorff. Simplest example is that if you take trivial topology, this is vacuously satisfied because only closed set will be non-empty closed set will be X, and there is no point outside that. So that is vacuously regular, but it is neither T1 nor T2. You have more than one point. Okay, so actually one reason is that we do not want to consider basically trivial space. Okay, in discrete space. That's why we put the conditions in that. Okay, regular space need not be T1 or T2. You can have still better example that regular space in that. Okay. Right, and I told you every metric space is a regular space. In order to, I told you the topologist, analyst of nowadays the trend is that minimum you need your space to be Hausdorff. Minimum you need your space to be Hausdorff. But in this case, look, regular, be careful, plus T1, regular plus T1. This is also called T3. Regular plus T1. T1, T2, T3. Why it is called T3? I will say. Okay. Thing is, now look. If you have regular plus T1, T3, then you see that points are closed. That means points can be separated. So it will be T2. That means T3 implies T2. And T2 implies T1. If you have regular plus T1, then points are closed. So that means by this points can be separated by open sets. That means it will be T2. So regular plus T1 will be T2, but only regular without T1, it need not be T2. Okay. Also you see that regular plus T1 is same as because if you have, look, this way is obvious, T2 implies T1, regular plus T1, I have seen T3, but I have got then T2, so this is true. So regular plus T1 will be regular plus T2, that means it's a Hausdorff. Here is a caution that if some books, by regular, they take actually T3 because their minimum assumption is Hausdorff or T1. So some books, when you are reading from a book, just see, Willard has taken separately. They have T1 regular and T3 is different. Okay, but some books, they by regular they mean T3 by regular. So that whenever you are starting a book in topology, see that what is the definition carefully, whether they are assuming in the beginning the spaces to be T1 or T2. But here my convention will be regular and T3 separate. Regular and T3 separate. So T3 will be T2, but a regular need not be T2. Okay, right. So that you should know. I think right now it will be enough on that. Okay, I don't need to spend much time, but I will tell you that what is the idea of the regularity and that I will tell you. Now, on the other hand, if I go for complete regularity, so that you should know, a regular space need not be T1 or T2, but regular plus T1 is called T3. Okay, and T3 is implies T2, and of course T2 implies T1. We are actually building a ladder. Okay, now completely regular, you see that I told you that here same thing, but you are separating by a continuous function. This is very important for both topology and analysis because actually later on see the minimum property topology a topological space should be completely regular. Then you can work a lot of things. So completely regular means, look, a topological space X tau is called completely regular if given a non-empty closed set C in X and X belongs to X minus C, there exists a continuous function. This thing. F X star to more specifically this with the usual distance, that is subspace topology, such that if C is 0, that is, it means if C is 0, we write often, means if C is 0, small c, for all C belongs to C, and Fx equal to 1, separating by a continuous function. Okay. Well, I told you last time, this is stronger than separation by open sets. I said there is no preference between 0 and 1. You can have 1 here, you can have 0 here, because I can have a composition of functions. Suppose you have this X F, I can have another function going to this. Don't to confuse with this X. You can take T, 1 minus T. So G dot F, if you take, then it will change. Then G dot F C will be 1 and G dot F X will be 0. Okay. So there is no preference. So don't bang your head whether you should take 0 here, 1 here, it doesn't matter. Okay, right. And that is one thing. Second thing is that I mentioned last time, that this interval, there is no special thing. You can take this interval also, such that Fc equal to A and Fx equal to B. That also told you that between A and B, same argument, similar argument, 0, 1. I have actually homeomorphism. Okay, Hertz was very worried about it. I don't need asymmetry. There is a homeomorphism actually. Particularly, you have a continuous function onto continuous functions. Going there. So you can take, you could replace by these also. Okay. So if you have this, then it is called completely regular. Now look, separation by continuous functions is stronger than separation by open sets, so that this one you don't need T1 here. Look, this is immediate result. Every completely regular space, look, if you have this, then it is separation by continuous functions. Yes, this is important. Then this will be separation by open sets. so that every completely regular space is regular. Okay. Here you don't need T1. Okay. Right. Now, here I should tell you that, but I am not assuming T1 or T2. In fact, completely regular that you need plus Hausdorff. We call it a T1. That I told you. We call it Tychonoff space. Tychonoff was one of the founders of topology. Actually, among the authors there are, because I think he was a Russian and that. There is a confusion about the pronunciation of his name, so that some people think it should be actually Tikhonov. In some books, I think this is correct actually. Okay, so Tikhonov, if you see some book, you should know this is Tychonoff. Okay, so completely regular plus T1 is called Tychonoff space. Now, completely regular plus T1 is Tychonoff. Look, completely regular. Here, let me tell you. Completely these will be all in syllabus. Plus T1 is the same as completely regular plus T2. Well, this way is obvious, but this way you can see that I told you that complete regular means actually regular plus T1. That I already proved. It is T3 and that implies T2. So it will be this. So for these spaces, if you assume extra T1 or T2, that is same thing. Okay, that is same thing. So that's why often we say let extra be a complete regular Hausdorff space. Okay. So this is called Tychonoff space. This is very important. Some people jokingly called it T3 and half space. That I will tell you that. It's why it is called T3 and half space, because there is T4 space and T3 and T4 came before this. It came later. So, but it was in between them. So how to place them? That's some people call it T3 and half space. But usually these days we do not call them. We call them Tychonoff space. Okay, right. So that now the thing is, what is the importance of this? Well, have you thought of, look, if you take X star, the topological space, okay, so you know all the constant functions. So take this, all the real valued continuous functions. Suppose f is constant. Any topological space if you take, it will be continuous, constant function. But actually, while studying, have you ever thought of the situation that whether you can have it, that only continuous functional topological space are constant? Only topology are constant. Suppose when this situation happened, the continuous implies this opposite.
Discrete topology.
Huh?
Discrete topology.
Discrete topology on the domain. Okay, fine. So discrete topology. How can you say that? I do not think you are right. Continuous functions are constant. Discrete topology, in fact, domain, any function will be continuous. Any function will be continuous. Any function will be continuous.
Oh, sorry, sir. Sorry, sir. Yes,
Then
yes.
what? Huh? In discrete topology.
Hausdorff.
Hausdorff only. How do you know that? If you have just Hausdorff, Hausdorff is a good thing actually. Points can be separated. So that the continuous functions will be constant. Well, simplest thing you look at that. Oh, sorry. If you take this x tau, trivial topology. Of course, x has more than one point. Now look what will happen. If I take suppose this is continuous. What will happen? Can it be? Will have to be constant. Suppose this is not constant. That means there exists x1, x2 in x such that, of course, fx1 not equal to fx2. Okay. Well, you can take 2 epsilon equal to then you have two open sets u1 okay. But this is a non-empty open set because fx1 is here, fx2 is here. But that means this will be non-empty. And only open set, non-empty open set is x. So this is x. This is also x. But that is not possible. Why it is not possible? Because they are disjoint. Has to be disjoint. The way I constructed. Have you got it? Okay. Right. So trivial topology is a function. That's why trivial topology is bad. Any continuous function will have to be constant. Okay. Any continuous function will have to be constant. Okay. It's a simple thing. You can't have it. Okay. Right. This kind of argument I often used in last semester also. Okay. Right. So look, fu1 will be yes, f inverse here. U1 is this, U2 is this, f inverse. Any point its image will be here, any point's image will be here. Okay, but they are disjoint. But here you are getting that both are going to fx and whatever is this, same set. Okay, so that trivial topology will be, but the thing is that can you prove it that? So if you have this trivial topology, if it is continuous, implies it has to be constant. But what about the converse? Can you prove the converse is true? Suppose I gave the question query. Let x tau be a topological space such that every real valued continuous function on X is constant. Fine. Is tau trivial? That's the question. Answer is no. In fact, right now I talked about regular 23. I can have a regular topology on which every continuous function can have a regular topology, regular non-trivial topology. You can have examples of there. Okay. On which every continuous function is constant, but it's not trivial topology. Well, I think this was given in by Hewitt. He was one of the biggest mathematicians the last century. I think year it will be 1946 or 1948. I think it was part of his PhD thesis. Okay, I'm not very sure about the year. I think it is 1948, not 46. It was part of his PhD thesis. So that this attracted attention. That's why completely. But what about completely? Look, the way I'm giving you the definition. Look, on the other hand, look, completely regular definition. Oh, sorry. Completely regular. Of course, you can assuming non-trivial topology, okay? Because trivial topology, every continuous function will be constant. So that non-trivial topology, in order to ensure, what does it mean? Non-trivial topology, non-indiscrete topology. That means you have open set other than X and phi. Open set other than X and phi. So that means X minus U is closed, which is neither whole X nor empty. Oh, पता नहीं कहां से आ रहा है. So this is closed. So you have to take a point outside. If it is a completely regular, then there is a guarantee that you have a non-constant continuous function. Non-constant continuous function. It is not only that you have non-trivial topology, you need to ensure that you have a good collection of continuous functions, particularly you have non-constant continuous functions. And that means there should be a rich collection of continuous functions, real valued continuous functions. So that if you have this, then complete regular by it will get, because on this it will be 0 or whatever is 0, and outside it will be 1 on the outside point. So that will be a non-constant continuous function. Okay, right? So that from the viewpoint of the continuous non-constant continuous function, this is required, this is minimum, because if for regular we have the examples. For the regular we have the examples that still regular non-trivial topology, still you have the possibility that all the continuous functions are constant. So that non-constant continuous function, if you want to ensure, you have to assume this is completely regular. Okay, plus T1. Of course, because you don't need T1. Okay, do you need T1? Non-trivial topology, you need basically completely regular. But completely regular, you need T1. Reason is trivial topology is vacuously completely regular. So that otherwise you have to say that non-vacuously completely regular. Okay, that we can ensure by assuming completely regular plus T1. Then I will have non-constant continuous functions. Okay, non-trivial topology, I'm saying non-trivial topology. I don't need T1, but I need to ensure non-trivial topology. Okay, but with T1, ensure that it will be non-trivial topology. Okay, but I need non-trivial topology. That's why the importance of complete regular. And complete regular plus T1 is called Tychonoff. Okay. Here again I am telling you that I told you complete regular plus T1 is same as complete regular Hausdorff. Some people by complete regular means complete regular and Hausdorff. Like I think Munkes also did that. Okay. So that be careful again. When you're reading somewhere, then that whether complete regular Hausdorff is there or not. Okay. Usually it will be given. So from the viewpoint of this, which is basically something minimum requirement, we assume our space basically minimum that x tau should be complete regular Hausdorff. So that our space should be usually a topological space x tau should be completely regular and Hausdorff, which is called Tychonoff space. So now look, this you have got Tychonoff space implies T3 space. So regular plus T1. Need that for Hausdorff plus T2 space implies T1 space. But for each state, it need not be true. That it converse. Reverse implication. You can always find example, counter example. You can look at Willard, you can look at Munkesh and that some books. This is not true. This is not true means there exists space in that. Okay, but this is true. Tychonoff implies T3, T3 implies T2, T2 implies T1. But T1 need not be implied T2. Okay. This one thing you already know that cofinite topology, that is T1, not T2. Cofinite topology if you take on infinite space. Okay, but T2 space, not T3. T3 not this. Okay, I'm not very much interested. You should look at, if you are interested, you can look at that counter examples. Okay, so this is Tychonoff space. You got it? Okay, now thing is that, but the first thing is, I already explained, metric space has this property. So that this has all these properties. Metric space has. But with Tychonoff space, we can work a lot. I will tell you something more than that after I talk about normal space. Look, in completely regular, I have separated a closed set and a point lying outside this. But what about separating two closed sets? So here is a definition of normal space. A topological space x tau is called normal if given any pair of disjoint non-empty closed sets A and B in X. There exist open sets U and V in X tau such that A is contained in U, B is contained in V, and this joint. That means you are having separation of closed sets by open sets. Okay. For empty set, you do not need to consider that. Will backwards it will come and then. So it can take non-empty closed set. This is called normal. Okay, right. Here it doesn't say it will be T1. Okay, so but if you take normal, that's why normal plus T1. I have not talked about separation by continuous function. That I'll tell you because that will be same because of the Eurytion's lemma. Normal plus T1 is called T4. Okay, right. Now look. Again, I am telling you that some people by normal they mean T4 space. The T4 space. Okay. Now the question is that whether T4 space implies Tychonoff or not. Look, points are closed by this T4. So that is I get this, but I get this thing. If you have right now only I have this much. So that means I get T4 implies T3. I do not get immediately this. Okay, I do not get that because completely regular, the first separation axiom where we are having separation by continuous functions. Okay, here I have given separation by open set, and for T3 regular I have separation by open sets. So since I am assuming it is T1, points are closed, so T4 will imply T3. Now this thing, T4 implies Tychonoff or not. That is the question, whether T4 implies in fact, I can ask something more than that, whether normal implies complete regular. This I can ask. Well, here I should tell you that Berkin saw there are two big theorems, Eurytion's lemma regarding normal space. Eurytion's lemma, they are misnamed, rather I will say that. And theorems are correct, proofs are correct. Only thing names and Tietze's extension theorem. This is. This I will teach you on Friday. But what about Eurytion's lemma? Okay. Well, let me tell you that. Look, these two theorems are big theorems. I won't give you the proof. I won't give you the proof. If you are interested, you can read the proof. You can ask me if you have some doubt, because most of you won't be interested in the proofs of that. And proofs are very tedious. But it will be good enough if you understand the results and if you can apply them. They are extremely important because you can apply them many places. In fact, you need them. Okay, not only you can apply them, you need them. So what is Eurytion's lemma on that? Let me tell you that. Okay. In Willard, I'm just giving you the page number. I will come later on to this, page 102. Okay, and this is 15.6. Okay, so he's saying the space means a topological space. A topological space x tau is normal. Here, let me tell you, if you are reading from Willard, you often will see the definition results two ifs. Basically, logicians they use it. It means if and only if. But usually these days topologists they don't use it. If you have two f, that means if and only is normal. If and only if I'm writing this. Whenever A and B, you can take them non-empty. A and B are disjoint non-empty closed sets disjoint non-empty you could take because empty backwards will be true. Closed sets in X is X star. There is a continuous function. There exists a continuous function f x2 the space 0 1 with this f a is 0. F a is 0 means for each point in A it is 0 and f is 1. Look, this is gives you separation by continuous function to disjoint closed sets. So in case of normal space, separation by open sets and separation by functions, continuous functions, they are same. That's why for normality you don't need two definitions. Look, that's why the definition of regularity and complete irregularity, they are different. Regularity gives you separation by open sets, complete regularity gives separation by continuous functions. So you have this. Okay, right? Fine. So look, if you have this, this is a big lemma. Make sure you don't forget it. And with this, see, every T4 space is T4 space is taken off like that. Okay, because points are closed. So this is yes by Eurytion's lemma. But what about this thing? Look, problem is that points whether closed or not. When you have normal, point need not be closed. Here I am having the closed. So Eurytion's lemma is not applicable here. Okay. So can you find a space completely regular which is not normal? Okay, that is the question. It's a big question I'm leaving it. So that in absence of T1, in absence of house drop, you should be careful. You should be careful. If you have house drop, then your life is nicer. You don't need to bother about. So that you are getting this thing. So be careful about this. But completely regular by also implies regular or not. Complete regular implies regular because look at the definition. So that this much we are getting. T4 implies Tychonoff implies this ladder we are getting. T3 implies T2 implies T1. But keep careful. T1 is there. If T1 is not there, you should be careful. Okay. And here you see this came later on. So some people call it now already 4 was there, 3 was there, they are well studied. Then they accommodate by this T3 and half space. That I am just giving you for the information. If you somewhere if you see that notation, it means Tychonoff space. But these days use Tychonoff space. And again I am telling you, let me finish this, that whenever you are dealing with your space and you want to use continuous functions, then your minimum assumption should be Tychonoff space. Minimum assumption should be Tychonoff space. That means completely regular Hausdorff space, which will give you a rich collection of continuous functions. As I told you, I will tell you one day that if you have a topological space X tau, then Cx, that I think last time I told you, is the collection of all, is the set of all real valued continuous functions on X. One day I will talk about this. Is very rich because this is a ring. This is a vector space. Many things you have Cx. So let me tell you that I am a topologist in the sense my actually area of specialization, particularly regarding my PhD thesis, is Cx. Anything with Cx I work. Later on I worked something different also, but my main area of specialization is actually Cx. I will discuss later on that. Okay, right. So Cx is very important because of Cx, I always need to assume Tychonoff so that I have non-constant continuous function. Okay, I would like to just mention, lest I forget, has nothing to do with this. Some of you are going for planning to go for higher study on that. If you are interested in that topology and that, you can look at applied topology, and particularly that is the, I think I'm not sure that how many of you are taking, or next year you can take that. Viplav Bosak is teaching a course in algebraic topology, in particularly applied algebraic topology. I'm just giving you the information. Well, if you want to apply algebraic topology, first of all, you need to know algebraic topology. It will be better if you get a chance to do such a course. I think this semester is offering, so I think next year you can take that, but this is optional. So applied algebraic topology, what they're doing these days, they call it topological data analysis. TDA, they call it. Sometimes they call topological data management, that is TDM. But here, basically it is part of applied algebraic topology. And here also they apply to neuroscience. That means medicine. In the US, some universities they have. One of your seniors here has gone to University of Florida to PhD here. But also there is another place I can tell you that. It is EPFL. This is the place. École Polytechnic School in Lausanne. This in Europe, polytechnic means technical school. It is not like India, the polytechnics. Okay. École means school. Basically university. This is EPFL Lausanne, Switzerland. This is a famous university actually. For any ranking and that, it will be in the top 20. Okay, one lady is there. She's an American professor. You can go to the website. Catherine Hess. I think she married some German Swiss and that. Another, she's an American. She did PhD in MIT. So actually, she did PhD in algebraic topology. She has a group there, and these days she's working on this. Okay, so I'm just giving you the information that some of you can think of that topological data analysis. Okay, but make sure that in order to do algebraic topology next semester year, you need to know topology well. Okay, don't think what I am trying to teach you abstract. I am not teaching you in abstract. I am teaching you very basic things which will require in other areas also, in function analysis also. That's why I will tell you that function analysis CX is very important. In fact, some good example, most of the time good examples come from CX. Okay, so see you on Friday. Okay, bye.